Hi everyone and welcome back. So in this video we're going to talk about another couple primitive data types. Okay, primitive data types, if you recall, these are ones built into the C language. Okay, so they're there by default, and we're going to use them later on to build more complex aggregate data types at another date. So these data types that we're going to talk about, these two data types, are both considered floating point numbers. And what I mean by floating points is this name comes from the fact that the decimal point seems like as if it can kind of float. So we're just talking about basically numbers that have information after the decimal point. So thus far we've been really referring to, when we look at integers, where we have, say, x, right, equals 5, etc. We're being limited in the fact that the range of these numbers, right, of our integers, right, it's when we look at the range of integers, right, we're not able to display or store anything that contains any sort of information after the decimal point, right? Just the definition of the set of integers, okay? So when we look at floating point numbers, we're able to store things like 98.6 or 666.667, etc. So we're storing that information, and we're going to do this using two different types of floating point numbers. These are referred to as single or double precision, okay, aka float and double. Okay, so we can store something like, say, float x equals 5.67, etc. Or the other alternative is to use something like double, okay, and do something similar, okay. Now, why do we have two different kinds? Well, it depends on the number of bits that we're going to be using to store this information, okay. Single precision is using 32 bits, okay. Double precision, the word double comes from the fact that we are doubling the number of bits to store the information, okay? So notice that here we're referring to 64 bits compared to single precision, which is 32. Okay, well, why does that matter, right? Well, it depends on how precise you need to be able to store the information, to store the number, okay? How much accuracy do you need? How much precision do you need after the decimal point? Okay, so let's just do a simple example to kind of illustrate this point. Here I'm bringing up my environment, and I've got I've got two different variables declared and initialized. I have num here, which is a type float, okay, and I'm storing it. I'm initializing it to 123.456789. Okay. Then I have another variable, numd, d for double, and I'm initializing it to the same thing. Okay, 123.456789. I am printing both of these numbers out to the console. Okay, one thing I want to point out here is notice these format specifiers. We've got, because these are different data types, we have different format specifiers for how we are printing that information to the console. Okay, %f is for float, okay, and %lf is for a double. LF comes from the term long float, okay, long effectively meaning double the bits. All right, long float is a double. That's the way of remembering that. You can also be able to reference it, and I'll provide a format specifier table for you to reference these things, which is kind of helpful when you're early on and you're not that familiar with them. But over time, as you're using them, you'll inevitably start just kind of remembering them. Okay, so we're printing both those to the console. I'm going to compile this, and let's go ahead and we'll run it too. And now you would expect that this is your intuition is going to be like, well, they're going to print the same thing, right? Well, your intuition is going to be wrong in this case, okay? And this illustrates a key difference between single precision and double precision. Let's look at these two numbers down here, okay? Notice there's a little bit of imprecision going on here with our single precision number, our float, single precision, 32 bits, okay? I initialize this to 123.456789, right? And notice we're getting the number back as ending in 87. Okay, there's a little bit of inaccuracy going on, and that has to do with basically that we're using 32 bits to store the information related to 64. The 64-bit option is more precise. In a future course, we will, and you'll actually, most students take this with me, take the hardware software interface class, we will go much deeper into how floating point numbers are stored in binary. All right, and there's also some ways in which they are computed in the computer hardware that's unique, different floating point operations, but that is for another day, right? Now, what we really need to know in this case, right, in the context of getting used to C programming, is the understanding of basically why are there two different data types for floating point numbers. And effectively that, for our cases in an intro class, we're really going to be able to use either one, okay? But this gives you a sense of what the difference is. And one is using more bits, but has greater precision. Well, you might say, well, why not just always use the one with greater precision? Well, when you're having more bits, right, that's more information to store, and it's also more complicated to compute things on it. It can be slower to have operations compute and to run when you're having more bits to process, okay? All right, so let's move on. Now, I want to point out here that when we have there's a couple conventions that are helpful. Okay. If I'm storing a floating point number, okay, and I have the number, say 5 to store, okay, good practice is to still do point with the decimal point 0, okay? It makes it very easy for someone reading your code to acknowledge that this is indeed a floating point. It's being stored as a floating point number, okay? Similarly, if I was trying to store 1/2, 0.5, okay, it would be deemed as good practice to put the 0, right, so that's easier to read rather than just writing 0.5, okay? So please include the decimal point, right, and have always a 0 on either side, regardless of the number that you're trying to use. It just makes it easier for you to avoid mistakes. It makes it very clear in terms of what data type you're initializing, what data type you're using. Okay, we'll go deeper into that a little bit later on in a subsequent video to look at how we kind of convert between different data types. All right, let's do an example. I think it's worth taking a moment and actually doing an example where floating points are necessary, and as well as just to reflect on a couple things that we've learned thus far. All right, the example I want to use is just to calculate an average. Okay, I want for this example we're gonna combine a couple things that we've seen thus far. We're gonna ask the user. We're gonna prompt the user to say, "Hey, how many numbers do you want to enter?" We're then gonna allow the user to enter a bunch of integers. Okay, based on that initial number, we're gonna then sum them up and calculate the average. Okay, so it's a little simple program, right, to calculate the average. So let's go ahead and let's code this, and I'm gonna come back a little bit later on to this example below that we were previously looking at. So what I'm going to do is I'm actually going to comment that out so that we can come back to it later on, later in this video and look at that as well. So, all right. So the first thing I need to do, right, is I want to ask the user how many numbers they want to enter. All right. So we're gonna ask the user. We're gonna say how many numbers. We'll just say how many numbers, right? And I'm going to use scanf, and I'm going to ask the user to initialize n, right? N for the number of, right? We could call this size. Maybe we want to call this, that might be a better name, right? How many numbers do we want to calculate as part of our average? Okay. I'm going to then have an integer sum. I'm going to initialize it to 0, and we're going to have a loop here, and that loop is going to continue to ask the user to enter a number, Okay. There, we'll say num. So continue to ask the user repeatedly for a number. Okay. And whatever they enter, we're going to just keep adding that to the, we're calculating a running sum, right? So we're saying the sum, right, equals the old sum plus the new number that the user entered. Okay. Now, to calculate the average, we need to take this sum at the end and divide it by the size, right? The number, the total number. Okay. Now, keep in mind, I'll use double here. I could use float as well. For the average, okay, I'm going to take the sum, all right, and divide it by the size. Okay, and then I'm going to print out the average. Okay, notice that I'm using the proper format specifier here because average is of type double. Okay. Now, I don't want to get too deep into this. There's some things that we're going to talk about later on related to data type conversions. But let's run this, and I'm actually going to change one thing here to, and we'll talk more about it later on. I'm actually going to change sum to type double, okay, and I'm going to initialize it to 0.0. Okay, that just makes it a little bit easier to recognize that that's a type double, right? The reason why I'm going to tell you later on, but it's going to avoid a problem. Okay, avoid a problem with how data types are stored. We'll save that for a subsequent video to kind of come back to this. All right. Now let's go ahead. Let's compile this and let's go ahead and run this and test to make sure everything's working properly. Okay. So how many numbers? Let's say we want to. We'll just do 3 numbers. Okay. And we'll let's calculate the average from 5, 7, and 9. Okay, we get the average is 7. Okay, we test it on a couple different things. Okay, 5 numbers, right? I'll just type in a whole bunch. And you notice that in this case, the reason I'm showing this example, right, is that okay, yeah, we're calculating it's a kind of an example that requires using floating point numbers to have a meaningful output, because even though we're having a bunch of integers being entered, right, the end calculation requires something that requires a floating point number, right? An integer cannot store 5.2. Okay, cannot store 5.2. All right, so that's let's move on. Let's talk a little bit. Let's do a little bit deeper into. Now we've seen this example of some things that can come up related to floating point numbers. For one, let's look at the context of some extreme values that can happen. Extreme values are things that usually indicate an error in your programming logic. Okay, you can get an infinities that come up based on integer division operations that take place. And there's really 3 different types of extreme values that you can get. Positive infinity, negative infinity, and NaN, which stands for not a number. Okay, so if you see INF, right, that stands for infinity. If you see NaN, it stands for not a number. If you get those, right, unless you're doing something really special, right, that tends to be indicating that you're having some sort of error, and you're and you want to kind of check if you're checking for, say, divide by 0 issues and etc. Right, that would be the big one, is checking that that you're not dividing by 0 and handling that occurrence correctly. So let's just take a look at some of these. Okay, at some of these numbers that can come up. Right, the first one is a pretty basic thing. Right, there's nothing really weird going on here. We have 13 as a floating point number divided by 3. Right, that's not going to do anything weird. Right, we're just going to get that as our result of that is going to be what you would expect, where you have 4.3 repeating. Okay, then get a bunch of 3s, etc. Okay, so that's normal, nothing weird on that one. Well, what if we had a divide by 0 problem in here, Okay. Well, in that case, you're going to get a value as infinity, INF. Okay. A couple other examples for dividing. If we do 0 divided by 5, well, nothing weird coming there. We're just going to get 0 returned, okay? But if we do something like this here, okay, we have an undefined result. This isn't an example of when you get something like not NaN or not a number. And I could show you some examples of that coming up. Some of these examples here. Let's actually even go back to our example of calculating an average. Okay, if we come back to this example here, right? I don't even have to change any of the code to get this to come up, right? I'm going to just run this again. Okay, and this time I'm going to do an example where we say how many numbers we want to calculate the average for. I'm going to type in 0. Okay, and notice in this case, we're getting this not a number. It actually gave a -2, but that's kind of irrelevant. We're getting a not a number come up because, right, we have size as 0 is entered, and we're initializing sum as 0. We have a divide by 0 problem. Okay, so we're getting that as not a number. Typically, the way that you address these is you check. Okay, there's a couple different ways. But you could say, well, hey, if the size is 0, you know, you can handle however you want that to be, right? Whatever you want the user to be able to see, okay? So here I'm just checking, right, if we're dividing by 0 and handling that occurrence correctly so that this not a number does not actually ever get displayed. That would be the proper way of handling that, okay? That's why I was saying before that those issues of seeing not a number displayed is usually an indication that there's some sort of error in your programming logic. Let's kind of go a little bit further here. Okay, so we're looking at floating point division. Checking that you're not dividing by 0 is an important step. Okay, there's one other important thing to note. Okay, so we know that in the context of integers or characters and a lot of the primitive data types we've looked at thus far, we compare them using double equals, right? So we've seen this before, and we know, like just like I did here, we're checking if size equals 0. We know that double equals indicates that we're doing a comparison. Double equals results in a true-false output, right? It either equals 0 or it doesn't. It's true-false. We're comparing, okay? Single equals is an assignment, right? We're taking everything to the right, and we're taking that value and we're writing it to what's on the left of the equal sign, right? So there's a big difference between single and double equals. We saw previously that a common error is to do something like this, where I have single equals in the conditional statement here, right? That's a very subtle bug that can drive you crazy. What that will do is actually set size equal to 0, okay? So be careful with that, all right? Now, why do I bring this up now? Why am I bringing this up again? Okay, we have if we go back to our old example, I told you I was going to come back to this, right? This example we looked at earlier, and we ran this example, right? And just to kind of refresh your memory, remember that the floating point number in this example showed some inaccuracy, and you can get that with double too, except you just have a lot more precision, right? You have a lot more accuracy because you double the number of bits. Okay, so we have this inaccuracy for floating point numbers, right? So let's just look at the floating point. Let's just look at this one number here, okay? And we know here that let's see what happens if I did this. Oops, I hit the caps lock. If I said num, we're checking if num equals this. Okay, and I'll just so we can see it, num is equal, and we'll say here not equal. Okay, now it looks like, right? It looks like if we look at this here, well, this is the same thing that I initialize it, right? Num is 123.45678.9. It's the exact same thing I initialized it here. Common sense would indicate that it should land here on line 10, okay? However, right, common sense is not correct in this case. So let's run it and let me show you and prove it to you. I run it. Notice it says it's not equal. Okay, well, that's weird, right? Well, the reason is we have this imprecision, right? We have this imprecision. Now, I promise you in a later course, you're going to actually get a much better understanding of why that's the case, okay? But we don't want to get into that now. All right, well, how do we fix this, right? How we fix this is we're going to use something called a function, and it's FABS, right? Stands for floating point absolute value. All right, so F for floating point, ABS for absolute value. And what we're going to do is we're going to take the number, we're going to subtract it by what we're trying to see if it's equal. Okay, we're taking the absolute value of it, so this way it doesn't matter if we're a little bit positive or negative, and we're going to check if it's within some sort of fairly close amount to that. So effectively what we're doing is we're taking the difference, right? We would take this number here, we're subtracting it of what we're checking to see what we're trying to compare if it's equal to, right? And we're seeing if that difference, the absolute value of that difference, is something pretty close to 0, all right? Some folks, you might have to include the math library for this, okay? Because that functionality for FABS is included in that. Now, by the way, this is a subtle thing. We could change this. You're seeing in my environment here, it's telling me that something's misspelled. Okay, we can actually change the settings to take that out. So just be careful. Not everything in your environment by default is indicating that you have an error. Okay, we should we change the settings to kind of get that to not display any misspelled things. So now let me run this. Okay, notice now it works. Okay, so here's the rule. Right, the rule is that when you're comparing floating points, right, use floating point absolute value. Right, it avoids the potential for subtle errors, subtle bugs in your code. Okay. Okay. I think that brings us to just double checking my notes to see if I forgot anything. I think we're good here on floating points. It's a kind of a breakdown of all the kind of essential need to know things related to using that. Essential primitive data type that are used constantly. And in the context of this class, I really don't care if you're using floats or doubles, right? We don't really care about having the double precision. We're also not doing high performance stuff that requires us to try to optimize things to not waste the extra space and compute time. So, all right. So thank you for watching. Feel free to ask me questions if you have follow-up, and we'll make sure that we're going to have some time for practicing these things later on in the course.